Hi guys, welcome back. This is the Chapter 9 content. We're going to be learning hypothesis testing, and most of which we have seen before, most of which we sort of know. In Chapter 8 we learned z-tests, t-tests, and population proportion z-tests. What we'll be learning new in Chapter 9 is something called the chi-square distribution. As you can see on the screen, it says 9.6 and 9.7, and 9.7 says Statistical Inference for population variance. Not quite sure why our book splits those up, but basically we use the chi-square distribution in order to make statistical inference for a population variance. So 9.6 and 9.7 should be the same section. You really don't have one without the other, and that's kind of that. So what we're going to do is learn kind of the 7 steps of hypothesis testing, which is not what you have in the book. The book advocates for 5 steps. We do things at the university or in the management department or the business stats course. We do the things a little bit differently. We think we do them better. So we're going to learn the 7-step hypothesis testing process. I think that you'll find that it's a very efficient one, and tends to be very procedural and just makes it really, really easy to organize thoughts, especially because we're going to be doing hypothesis testing in Chapter 9, 10, 11, and 12. So we're going to be doing it for the rest of the course. And the 7-step process really gives you an opportunity to think about all the problems in like the same logical manner. So whereas the distributions that we are going to be using changes, or the tests that we're going to be using changes, or even the structure of the problem, what's not going to change is that we're going to have a 7-step process for which we think about these problems, and it's just going to make it really easy for us to then set up a problem and then do our analysis and draw conclusions on that problem. So without any further ado, we'll go ahead and get started. I'm just going to quickly run through the PowerPoint slides, and then we're going to pretty much just go to the worksheet and I'll kind of teach from there. So what you're going to need when watching this video, just sort of as always, you're going to need the exercises sheet that can be found on Springboard. You're also going to need the appendix. So you're going to need to be able to have the z tables, the t tables, and now the new table, which is the chi-squares table, which that operates very similarly to the t table. You get a degrees of freedom, you kind of go and look up an alpha level, you hone in on a number, and that's your number. Okay, so we're going to be using the z tables, t tables, and chi-square tables, so have that out. And I believe, and then also have your grid out. The grid was this document. This is the one that I had just posted. I forget where I posted it in Springboard. It's either under Chapter 7 and 8 or probably not under Chapter 9. Maybe it's just under Unit 2. But I think it's labeled Grid 7, 8, 9. And this just has all the formulas that you're going to need for this unit. So for this test, this might be a good thing to have alongside of you when you take the test. So it has all the new stuff from 9 as well. So 6, we have the chi-squares, we have the population proportion, the t, and the z. Okay, but it also has all your 7 and 8 stuff as well, all the 8 confidence intervals, and all the z new sampling distributions and whatnot. Okay, so let's get started on hypothesis testing. Again, I am going to go through these PowerPoint slides rather quickly because I think it is most helpful to just start doing problems and run into issues then, and then solve the issues, and just kind of do it by attrition. So the first thing we want to talk about is the different types of hypothesis testing that we're going to be looking at. First of all, when you set up a hypothesis, which is going to be step 1 of the hypothesis testing process, when you set up a hypothesis, you're going to be doing it about some population parameter, some characteristic of the population. For the z and the t tests, not surprisingly, we're going to be doing this about mu, right? So just to take a quick aside, what we did in Chapter 8 was we used a sample mean, so an X bar, and then we added or subtracted, so we plus or minused a certain number of standard deviations to make an interval. The whole point of making that interval was to try to estimate somewhere that mu, the population parameter, where that could be. Right? So we did that with the z-test and the t-test, so we were trying to estimate where mu could be. Well, we also did that with p-values, or I shouldn't say p-values. We also did that with a population proportion as well. With data that's more qualitative in nature, it's more binary in nature, yes or no data, we made a confidence interval, and we said p hat plus or minus some form of a standard deviation, and then we made an interval. And so then that interval gave us a certain level of confidence where we thought p, the population proportion, was actually going to reside. So the whole thing about confidence intervals was to estimate where we thought the population parameter would be. So either mu or p, depending on what we were looking at. Okay, so hypothesis testing takes it a step further, right? So confidence intervals are great, but what you would notice is that we would go and we'd get these confidence intervals, and we would kind of have a huge gap. There would kind of be a large interval. So it's like, yeah, we have 95% confidence that mu is within, 20 units of the X bar or whatever. Okay, but maybe 20 units is way too big of a range for us to like have it carry any weight, to have it have any value. Or maybe when we're looking at p-value, the population p-value, we want to know where that's at. And we took a smaller sample and we got a p-hat of, say, 0.44. But then when we did our 95% confidence interval, that came up with a range of 0.25 to 0.59 or something, right? So like we have this huge interval to where we think that p actually resides, and so then it's just not that helpful. Okay, so hypothesis testing takes it a step further. The whole point is that we're going to be trying to prove or disprove something that we believe might be the case about the population parameter. So about mu, about p, or eventually we're going to see with the chi-squares distribution that we can actually look at the population variance, so sigma squared. Okay, so the three types that we have are greater than, less than, not equal to, and this is what these hypotheses are going to look like. The mu naughts that we see, so when we look at these hypotheses, this would read H naught, that's 0. The 0 subscript is read as naught, N-A-U-G-H-T, naught. H naught is mu is less than mu sub naught. Okay, whenever you see mu sub naught, that's going to be an actual number that is either assumed or given to us in a problem. Okay, so that's just going to be the assumed value. So our H naught kind of stands as our status quo, and that's just what is believed to be true. So if we believe that there's some population mean out there, then that's what we believe to be true. HA, which really is what you're going to be kind of like looking to determine if it's reasonable, is the alternative hypothesis, HA. And that's what we suspect to be true. So H naught is the status quo. HA is what we suspect might be the case. Okay, so there's three types. There's one-sided, greater than, one-sided less than, and then two-sided, which is not equal to. So the way that we determine these is we first look at what we suspect to be true. So we're actually first looking at the HA, and we would write out what our HA is. And then H naught is just going to be the complement of that. It's just going to be the opposite of that. Okay? And we'll get into what that looks like. We're going to do a bunch of problems today, and you'll see exactly what we mean by that. So what we just looked at was number 1 in the hypothesis testing process. So I'm just going to briefly explain how this goes, and then we'll move on. So state the null and alternative hypothesis, and yeah, that's what we just did. 2, we're specifying the significance level alpha. So what we did in confidence intervals is we had a certain level of alpha. If we had a 95% confidence interval, our alpha level was 0.05. If we had a 99% confidence interval, our alpha level is 0.01. So the alpha level is just specifying our chances of being wrong, right? So the smaller that alpha level is, the better off we are in being correct. Okay, so what we would do in step 2 was we predetermine what we want. So either in a problem it's given to you, or like say in your case, you decide what alpha level you're using. Are you going to use 0.05? You're going to use 0.01? Are you going to use something else? But generally 0.05 and 0.01 seem to be the generally accepted alpha levels that people use. So in number 2, we would just simply state what the alpha level is. Alpha equal 0.05. Number 3, select the test statistic. So depending on what we were looking at, depending on what the problem is asking for, we just select our test statistic. Is it going to be Z? Is it going to be T? Is it going to be Z with the population proportion? Or is it going to be chi-squared because we're using, or because we're looking for, to prove something about the population standard deviation or the population variance? Okay, so that's number 3 is when we determine what the test statistic is. Number 4, we determine our rule for rejecting H0 or HO. Okay, so what's going to happen in number 4 is we're going to draw a picture of the potential graph, right? So with Z, T, and chi-squared, there's a general shape of the curve. So we're going to draw that curve, and we're going to write in where our rejection region is, and we're going to write out the critical value, which I'll explain what that is in a little bit, the critical value that establishes our rule for rejecting H0. Okay, this is going to be a value that you're kind of benchmarking what your calculated values are. So you're going to have 2 different values given the distribution that you're using. If we're working with Z values, we're going to have a Z critical value, or we'll call it Z crit. And then we're going to have a Z data value or a Z calculated value, right? Those are Z data, Z calculated. I might use those terms interchangeably. They're the same thing. But so we're going to have one that's calculated, one that's critical value, and this critical value is the one that we're kind of benchmarking against, saying if it falls past this, it's in a rejection region. If it falls short of this, it is not in a rejection region. And then, so number 5, collect the sample data and calculate the value of the test statistic. So this is the part in the problem where you've kind of read through the problem, and now what you want to do is kind of go back to the problem and pluck out all the information that you need, write it down, and because we determined what test statistic we needed in step 3, we're going to then implement all the data that we have into that test statistic and then come out with our Z data or our Z calc or whatever the test statistic is, calculated value. Okay, based on that calculated value and based on that critical value. So essentially you take the information that you have from number 4, the information that you have from number 5. In number 4 you have the critical value. Number 5 you have the calculated value. And then in number 6 we're determining, well, what's our decision? Are we rejecting H0? Are we failing to reject H0? Okay, so we make our statistical decision in step 6. And then in step 7, we just put that into real world terms. Okay, so we made our decision in 6. Now we kind of go back, read the problem, and say, okay, yeah, we rejected this, and we did this in statistical jargon and all that. But what does this mean in terms of the problem? Okay, and that's what happens in step 7. Okay. So here is an example of the Z test statistic. If you want to quickly look at your grid, that might make it easier because it'll show you all the test statistics. Those are just the slides. And we have a Z test. I'm really not going to go through these too much, I don't think. You guys can read through these, but you're very familiar with the Z test. We did that in Chapter 7. We did that in Chapter 8. We learned the distribution in Chapter 7. We learned the confidence interval in Chapter 8. And for Chapter 9, like, you understand how to use it. You really just need the formula. P-value, this is something that we're going to get into more in Chapter 10 and more when you're using computer output. So p-value, so we've talked about alpha. Alpha is like our level of rejection, right? So It's the amount of probability in that little tail of the distribution that we're saying we're kind of reserving that to be wrong. We want that as small as possible generally, but that's like the amount of probability that we reserve to be wrong. So the smaller the probability is, the less likelihood that we're going to be wrong given the running of the test. Okay, so p-value, what happens with p-value is you could run a test in Megastat or a test in Excel somehow, and what it'll spit out to you is a p-value. Okay, the p-value ignores alpha and just bases their calculation on the test statistic itself, and it tells you, based upon that test statistic, what the probability is that you would be wrong. Okay, so what the probability is that essentially, well, yeah, we'll get into that a bit later. We'll get into that a bit more when we're working with the computer output. I don't really want to spend too much time on this, as in this chapter I don't think we're going to be working with it at all. You will see it somewhat in your case, but p-value tends to be fairly easy to interpret when you have like sample data and sample statistics that you run that tend to be very different from the assumed population statistic. You're going to notice very, very, very small p-values, and essentially that represents the probability that the population parameter is still correct. But you would assume that based on the fact that like your sample is just so far from what the population parameter is. So that tends to be the logic there, but we'll get more into that when we're actually working with the p-values, but this is just something that we bring up in 9. Okay, so this just talks a little bit more about p-values, but can also be applied to alpha level. When a p-value is less than 0.1, some evidence of rejecting H0, less than 0.05, strong evidence, less than 0.01, very strong, and less than 0.001, extremely strong evidence for rejecting H0. Again, we'll get more into that when we do computer output. Here's the t-test. This is for sigma unknown. This is what we learned in 7 and 8 as well. So I won't spend too much time on this. You guys know this distribution. So if you have questions on it, either leave them in the discussion forum, or just go back to your 7 and 8 notes, or go back to the grid, or anything like that, or any of the old videos, and kind of look into the t distribution. More on the t-statistic. And now the z-test. That needs edited. Z-test tests about the population proportion. Yeah, so these are formulas that you know. These are formulas that you've seen. So this is in your grid as well. These are the assumptions for independence. And these are just some rejection regions that we have. Okay, so we'll get more into that, or well, we don't really have to get more into that. You guys have seen this, and we'll get more into like the H0 and the usage of this test statistic when we're working with it, solving the problems. And now the distribution that you've never seen. This is the chi-squared distribution. This is solely used to test variance, nothing else. Variance / standard deviation, essentially. And the distribution, or the probability distribution function, or the graph, you know, looks like this. Okay, and the formula is coming up. This is the formula for the confidence interval, but this is the formula for the distribution itself. It's actually a very simple formula. So to calculate your chi-squared calculated value, it's just going to be the degrees of freedom, which is n-1, times the sample variance over the assumed population variance, sigma squared naught. Okay, again, we've got some pictures of, looks like rejection regions, and I will show you a little bit more how to use those. Okay, all right, so let's go over to the worksheet, and we're going to start out with z-tests, because that's what we, I guess, are most familiar with. That's the grid. So have your grid out. Have your grid out, have your statistical appendix out, have your worksheet out, have all of it out. Okay, So your worksheet's going to look like this. It's going to go over some of the notes that are in the PowerPoint slides and kind of explain them a little bit further. Okay, so we'll just start with sample problem 1. A production line operates with a mean filling weight of 16 ounces per container. Overfilling or underfilling presents a problem, and when detected, requires the operator to shut down the production line to readjust the filling mechanism. From past data, a standard deviation of 0.8 ounces is assumed. A quality control inspector selects a sample of 30 items every hour, and at that time makes the decision of whether to shut down the line for readjustment. The significance level is 0.05. Okay, so for A, the 10 a.m. sample indicated a mean of 16.32 ounces. Conduct the appropriate hypothesis test. What should the operator do? Okay, so the first thing that I want to talk about that I think clues us into kind of what's going on here is this overfilling or underfilling. Okay, that really clues us into this test being two-sided, right? Because when we're looking at what our sample could be, the decision that they are going to make to shut the line down is going to depend on whether something is vastly over what it should be or vastly under what it should be. So to me, that lends itself to us just saying, like, I'll just write down two-tailed. Okay, and another thing I would notice is that it says, from past data, a standard deviation of 0.8 ounces is assumed. Assumed is a very important thing here. Assumed means that we're talking about a population statistic, right? So when it says standard deviation, we're not talking about S, we're talking about sigma. Okay, so those things are very important. So what we're going to go ahead and do is get started on the hypothesis testing process. So we have A, and so then we'll just do step 1 is coming up with our H naught and our HA. Regardless of the order, HA is going to be something that we always do first because the status quo is not always going to be obvious exactly what the status quo portion of the hypothesis is saying. Sometimes you'll say that we believe that a mu is a certain number, but it kind of depends on which way you kind of expect that it's going in terms of how you write out that hypothesis. And you'll see what I mean as we go along. But so in generally, we want to look at what HA is first, what the alternative hypothesis is first. Okay. So what we're doing here when we're looking at this problem is we want to know, is this thing underfilling or overfilling? Okay. In general, is the population of this underfilling or overfilling? Well, underfilling or overfilling would mean that it's vastly different than what we assume that it should be. And what we assume that it should be is 16 ounces. So underfilling or overfilling implies that this is going to be a two-sided test. And a two-sided test is a equals or not equals test. So our alternative hypothesis is going to be mu is not equal to 16, which is the assumed mean. And then H naught is going to be, is a colon, is going to be the opposite of that, or the complement of that. So mu is equal to 16. So that's our hypothesis. And then we will look at what number 2 is. So number 2, if we look back at our hypothesis testing process, I guess I will go up so that we have this on point. Number 2 is what is specify our significance level alpha. Okay, well, it gives this to us in the problem, so we don't have to make any decisions about that. You'll find that that's kind of a common theme. So alpha is going to be 0.05. That's number 2. That's all we do. Number 3, select the test statistic. Okay, so first of all, we're looking at determining something about mu. Okay, so if we go to our grid here, we have 4 distributions that we can use in Chapter 9 for our hypothesis testing. We have test about a population mean, test about a population mean, z-test about a population mean, t-test about a population mean, z-test about a population proportion, or chi-squared test about a statistical inference of variance. Okay, so what are we looking at? We're looking at mu. So we're looking at population mean. So we automatically know we're not going to be using population proportion, and we automatically know we're not going to be using chi-squared because we're not looking at variance. So we're either going to be using the z-test about a population mean from 9.2 or the t-test about population mean from 9.3, which the formulas are shown here, z data, t data. So go back here, and what are the differences here? Well, for the z-test, just like in confidence intervals, the z-test, we assume we know a population standard deviation. For the t-test, we don't know a population standard deviation. Okay, so what do we do in this problem? From past data, a standard deviation of 0.8 ounces is assumed. We assume a population standard deviation. So this tells us that we're going to be using the z-test. And that is z data is equal to x bar minus mu sub naught over sigma divided by square root of n. X ar minus mu sub naught over sigma divided by the square root of n. And so number 4, determine the rule for rejecting H naught. Okay, so now this is when we get into the fun part. So the rule for rejecting H naught. Let's see if I can draw in here. I haven't done this in a while. There. So this is our normal curve. And we have an alpha level of 0.05. So the first thing I would notice is that this is a two-sided test. We know that this is two-sided because we're looking at overfilling or underfilling. We also know that it's two-sided because it was overfilling or underfilling, we made our hypothesis as such. Our hypothesis is an equal, not equal scenario, which means this is two-sided or two-tailed. So I'm just going to write in two different tails right here. Now, we look to our alpha level to determine how much probability is in each tail. Okay, so we have alpha of 0.05, which means that that's our chances of being in a rejection region. Because there's two different tails, we divide that alpha level into each of the two sides. So this side has 0.025, this side has 0.025, and then we know that the inside has 0.95 of the probability. Okay, so now what we need to do is we need to find z-values that associate themselves with these spots on the curve. So we did this in confidence intervals a bunch, so I'm not going to go over how to do this. I'll just quickly say we can find this z-value by just looking on the table where 0.025 of the probability is below it, and then this z-value by looking where 0.975 of the probability is below it. We've done this. We know how to do this. If you still have questions on this, go back to the materials in 7 and 8 and learn how to do that. Okay, these numbers are just going to be the positive and negative version of each other because this is symmetrical, and we actually know these numbers because this is something that we worked with in confidence intervals a bunch. So this is going to be z is equal to plus or minus 1.96. Okay, and then our rejection region, we say reject H naught if z calc, so this is going to be z crit, we call it, if z calc is greater than z crit positive, which is 1.96, or if z calc is less than z crit negative, which is the negative 1.96. Okay, so the next thing that we do is, so that was our establishing our rejection region. The next thing we do is number 5. Collect the sample data and calculate the value of the test statistic. Okay, so number 5. What data do we need to collect? Do we have all the data that we need? Let's see. So we know from the test statistic we're going to need x bar, mu naught, sigma, and n. So let's just write those in. X bar, mu naught, sigma, and n. And let's just go up to the problem and find out what these values are. Mu naught is the assumed, right? So we actually have this in the hypothesis here, but it's also in the problem. So 16, that's what mu naught is. Okay, x bar is our calculated sample, our sample mean. Where was that? That's somewhere, oh, that was given to us in A, so 16.32 ounces. Okay, 16.32. Sigma was that assumed value of 0.8. It's in the problem. And N was the sample size, which was given to us in the problem of 30. Okay, and now we actually have to calculate the test statistic. So the test statistic we established in number 3, right? So we're going to say Z calc is equal to 16.32 minus 16, I'm just following along the formula from 3, divided by 0.8 over square root of 30. And that value is going to be 2.19. So number 6 now, so this is Z calc, 2.19 is Z calc. Number 6 is decide whether or not to reject H naught. So make our statistical decision. Okay, well, the way that we decide to reject H naught is we look at number 4 and we say, well, how does this apply to the rules that we came up with? Is it greater than Z crit positive, or is it less than Z crit negative? It's not less than Z crit negative, right? It's not even a negative number, so we don't have to worry about the second one. Is it greater than Z crit positive? Is it greater than 1.96? Yes, it is. So then our decision is reject H naught because Z calc is greater than Z crit positive. That's to say that 2.19 is greater than 1.96. And then number 7, I guess I'll just write up here. So what is our managerial decision? Interpret the statistical results in managerial terms and assess their practical importance. I guess I won't write it down. I guess I'll just talk through it. Well, what was the idea of this problem? The idea of this problem is if we find this thing to be overfilling or underfilling significantly, right? If we have evidence that the population parameter of mu, meaning like what it's really doing, not like the data that we get or anything like that. We're using that data that we get to figure out what is the population really doing, like what is the machine actually doing. Not just like what is the couple pieces of evidence we pulled from it, but what is the population actually doing? We're using that statistical evidence to determine what is the population actually doing, and if it is habitually overfilling or habitually underfilling, we are then going to shut it down. Well, we determined that yes, we don't think that mu is equal to 16. We actually think that it's higher. So we actually have to shut the machine down. So we'd say, we rejected, so in 6, we'd say we rejected H naught because of this, this, and this. Z calc is greater than Z crit positive. And we've determined that we think that the machine is overfilling, and thus we're going to shut it down. That's that. Okay, so for time purposes, I'm not going to go through B. I'm really just going to hit probably problems 1, 3, 5, and 7. So I'm just going to give you each problem or just one problem from each section. But then I think what I'll do is I'll make available the answers to all the problems. Just because this video will just get absurdly long if I walk through every single one of these problems. Though, please feel free to ask me questions. Though I think with the hypothesis testing process being the way that it is, it's very easy to follow along to determine where certain values came from. Okay, so I'm not going to go through B, though what I will say about B is B only gets different at step 5, right? So B says the 3 p.m. sample indicated a mean of 15.82 ounces. Conduct the appropriate hypothesis test. What should the operator do? So the only thing that we're changing is that piece of information. Literally all the other information that we have is the same. So everything up through 4 is the same. Same hypothesis, same significance level, same test that we're going to be using, same rejection region. And then we look at 5, and the only thing that actually changes about 5 is, well, we're using a different X bar, right? And so then now this X bar is going to flow through to the Z calculation, and it's going to give us a different Z calc value, and then we potentially may have to make a different decision whether to reject or fail to reject or not, and then essentially a different managerial decision. Okay, so go ahead and work on that one on your own, and then whenever I can get the notes up and help you out in that way, whenever I can scan them in and get them up, you can check your answers against that. But for now on, we're going to move on to question number 3. Okay. Sample problem 3. The Motor Trend New Car Buyer's Guide listed the Ford Taurus as having an average highway fuel efficiency of 30 miles per gallon. A consumer interest group believes that the actual MPG is less, and that Ford may be overstating the miles per gallon rating for this model. A sample of 50 mileage tests with the Ford Taurus showed a mean of 29.6 miles per gallon and a standard deviation of 1.8 miles per gallon. Conduct the appropriate hypothesis test at alpha level equal to 0.01. What conclusions can be drawn from this? Okay, so let's first look at what our hypotheses are. We can do that, or we can look in the problem and kind of pluck out some results. But I guess to stay consistent with our hypothesis testing process, we're going to start just with step 1. And there we go. And so what are we saying here? What is this? What do we suspect? Well, we suspect that Ford is overstating the miles per gallon. So what does that mean? That means that we suspect that the miles per gallon is actually less than what they're saying that it is. So we suspect that their mu is less than what they say it is, which is 30. So then, conversely, H naught is going to be mu greater than or equal to 30. So the status quo is that the miles per gallon is greater than or equal to 30. Really, in the problem, it just says that they're advertising it as equal to, but this is kind of what I was talking about in the last one. We want to establish what our HA is first, our H alternative is first, and then H naught is going to be the opposite of that. So that's that. So number 2 is when we look at what is the significance level. Well, that's given to us in the problem. So we have alpha of 0.01. Number 3 is what test are we using? We know that we're looking at mu here, right? So of the 4 tests that we're learning in Chapter 9, 2 of them deal with mu, the z-test and the t-test. We don't have to worry about the z-test for population proportion or the chi-square test for variance. Okay, so we're looking at either z-test or t-test. What are the 2 factors that determine whether you use a z-test or t-test? Z-test is when we have a known population variance. T-test is when we don't have a known population variance, or we only have a sample variance. Well, in this problem, it mentions nothing of a population variance. It only mentions a sample of 50 mileage tests with the Ford Taurus showed a mean of 29.6 miles per gallon and a standard deviation of 1.8 miles per gallon. That's from the sample, right? So because our population standard deviation, because our sigma is unknown, we have a known S, right? We have a known sample standard deviation. But because our sigma is unknown, we're going to be using the t-test. That's a t. Which that statistic is t is equal to x bar minus mu over s, not sigma, square root of n. Okay? And the answer is yes. You always have to use the 7-step process when dealing with hypothesis tests. So just deal with it. It's all right. Okay. So in 4, we're establishing our rejection region. So we draw that. Now this is different than the last problem. This is one-sided. And what we do to look to see where the side of the rejection region is, we go up to our hypothesis, so we look at our HA. Our HA is pointing to the left, right? It's a less than probability. So our rejection region is going to be on the left side. Okay? And my phone just went off. Let's see if it's important. No. No. Okay. Still no. All right. Okay, so, and then we want to establish how much probability to put in our rejection region. We look at alpha for that. So we have 0.01 in this rejection region. Okay, so we have 0.99 in the non-rejection region. And now we need to determine what critical value. Right, so in the z-test, it was very easy. We just used kind of those numbers that we used from our confidence intervals, because we're very comfortable with alpha levels and determining what z-values are. We're very comfortable at going to the table and doing that. T-test, we did that a little bit in Chapter 8, but we'll go ahead and show you how to do that again in 9 just to kind of refresh your memory. So we need to find out what the t-crit is for this point right here. So t-crit is going to be the t value such that we include the alpha level, so 0.01, or the alpha level on one of the tails, and then the degrees of freedom. So here I'll just write, rather than 0.01, I'll write alpha df, which is equal to t of 0.01 in the degrees of freedom. Do we remember what degrees of freedom is? Degrees of freedom is just n minus 1. It's just the sample size minus 1. So in that regard, it's going to be 50 minus 1 equal 49. So it's going to be t of 0.01 comma 49. Okay. So then now we go to our table. This is a z table. We want to be on the t table. We want to look this up. So we're first going to look for our degrees of freedom. Because this one goes up to 48, so we're on to the next table, which is still t. 49, we found it. And then we're looking for 0.01 on one of the tails. So 0.01, t of 0.01. So degrees of freedom 49, t of 0.01. We have 2.405. Okay. So then, and that's a negative number, right? So in the table, it's going to give you all positive numbers. It's assuming that the tail that you're looking at is the right-hand tail, but because the t distribution is a symmetrical curve, anything that you have on the left-hand side is just going to be the negative number. Okay? Okay. So now, we've shown our rejection region, and then let's just write our rejection rule. So we'll just say reject H naught if t calc is less than t crit. Okay? And that t crit is equal to negative 2.405. So we've established our rejection region that we're supposed to do in number 4. So now, oh goodness, this pen, I swear. Now we go to number 5. Number 5 is when we collect our data and calculate our test statistic. So what data do we need for our test statistic? We need x bar we need mu sub naught, we need n, and we need s. Okay, I'll let you guys look up at the problem and find these different values, but we know that x bar is the sample mean of 29.6, mu sub naught is the assumed value of 30, n is the size of the sample, which is 50, and s is the sample standard deviation, so the standard deviation that was calculated in the sample, so 1.8. So now we're going to calculate t-calc or t-data. I know I use them interchangeably. T-crit is the only one that stays. T-crit is always t-crit. Okay, but t-calc and t-data is used interchangeably. Okay, and then so then we have 29.6 minus 30 divided by 1.8 divided by the square root of 50. This whole thing is going to shake out to be negative 1.57. So that's our t-data or our t-calc. Okay. Okay. So now we've calculated our test statistic. So we're going to decide whether or not we're going to reject. And we do that by determining, does this meet the criteria to reject? We said reject if t-calc is less than t-crit of negative 2.405. The answer is no, it's not less than. 1.57 is like somewhere in here, so less than would mean that would be more left. It would be more negative. It would be a higher negative number, right? So we fail to reject there. So we'll say FTR, failed to reject, because t-data is not less than t-crit, which is to say negative 1.57 is not less than negative 2.405. And I don't do greater than, I do not less than, because that kind of just emphasizes what we're trying to show, as opposed to like greater than, less than. It kind of gets ambiguous or kind of gets hard to follow. Like when we say not less than, it's showing that we're failing to do what we tried to do, as opposed to just making a positive statement, which then it's kind of ambiguous. Like, wait, were we less than? Were we greater than? This is saying that like we failed to reject because we didn't meet the criteria, right? That's all. And then we go on to number 7. Number 7 is, hey, put it into managerial terms. And the only thing that we can, what we would say is that because we failed to reject, we cannot conclude that Ford is overstating their miles per gallon for the car. And that's that. I won't write it in because for some reason it's just a lot more comfortable to write math than write sentences on here. But yeah, we just say we cannot conclude that Ford is overstating its miles per gallon. Had we gotten a t-data or a t-calc value that was more negative than negative 2.405, then we would have been able to conclude that they were overstating and that the actual miles per gallon was less than what they were stating that it was. Good. Let me know if you guys have questions on that one. So now we're going to skip down to number 5. So number 4 is just another example of the t-test. So now we're going to go to number 5, which is obviously going to be the population proportion test. Shell Oil office workers were asked which work schedule appealed most, working 5 8-hour days a week, the current schedule, or working 4 10-hour days a week. Shell management is trying to obtain statistical support that shows that significantly more than 50% of office workers prefer the 4 10-hour day work week before making any changes. A sample of 105 workers showed 67 preferred the 4 10-hour day. Conduct the appropriate hypothesis level at alpha level of 0.05. Okay, so before we even get started on the hypothesis test, I want to talk about why we know not just because it's in this section of the exercise guide or review guide or whatever you want to call this. We want to talk about why we know this is a population proportion problem and not some X bar mu type problem like Z or T. We know that this is a population proportion problem because we have a certain sample that is based on like kind of a qualitative variable. It's kind of a binary variable, right? Like this, it seems like the survey happened. What they're trying to determine is, do our employees feel this way or the other way, right? It's kind of a binary scenario, and it's kind of a qualitative scenario. So that qualitative nature of it lends itself to us finding a proportion, because either somebody feels a certain way or they don't. Right? And so then we can just say, well, a certain percentage feel this way and the other percentage doesn't. Okay? So that in and of itself lends itself to it being a population proportion, as opposed to it being all numerical data where when you take a sample you get some like mean. Right? There's no mean here. This is a proportion. Right? A proportion feel a certain way. It's not like that they're collecting a certain number. It's not like that they're collecting 105 pieces of numerical data. They're collecting 105 opinions, right? Well, I prefer the 10-hour workday. I prefer the longer workday and the shorter number of days or whatever. So that's how we know that it's a population proportion problem. That's what you're looking for. Is there a proportion that's happening here? Is it a qualitative variable in nature? Like, are they looking, is it a yes or no kind of thing? That's how we know that it's a proportion. Okay, so once we've established that, let's just get started on our scenario here. So let's get into number 1, which is determining the hypotheses. Okay, because we now know that we're working with a proportion, we know that our hypothesis is going to have to reflect that. So first, we want to look at HA, and that's what do we expect is going on, okay? Or what do we suspect is going on? So not the status quo, but like what are we trying to prove? What are we trying to figure out if it's going on? And it says show management is trying to obtain statistical support that shows that significantly more than 50% of office workers prefer the 10-hour workday. So we're trying to show that P is greater than 0.5. And then conversely, H naught then is P less than or equal to 0.5. Okay. So number 2, what is our significance level? Well, that's given to us in the problem. We have an alpha level of 0.01. 3, what statistic are we working with? Well, because we're working with P, we know that we only have one statistic to work with, and that's our Z value is equal to P hat minus P naught, and all over P naught 1 minus P naught N, and that whole thing is under the square root. Okay, so 4 is determining our rejection region. So because we're working with a Z, we're working with normal curve, right? And we look to our HA to determine where the rejection region is. So this is pointing to the right. So rejection region is over here. So the rejection region is right there. And how much probability do we have in the rejection region? We look to our alpha. So we have 0.01 here, which means we have 0.99 here. So what Z value has 0.01 of the probability above it and 0.99 below it? So let's look on the table. This is not going to be the same value that you're used to using for the 99% confidence interval, right? The 99% confidence interval was the one where 0.005 of the data was above it and 0.005 was below it on the negative side. This would be more akin to like a 98% confidence interval. So we'll go ahead and we'll look at our statistical table here. And so we're just looking where 0.01 of the data is above it, or really where we're looking just at is 0.99. So we're looking here, 2.0, kind of running across. We get to 0.98, 2.1, 0.9857, 2.2, 0.989, we're getting much closer, 2.3. 98989901. So that one's the closest, I would say. So that is 2.33. 2.33. So our Z crit is 2.33, which is a number that we've worked with before. We recognize that number. So what is our rejection region? So our rejection region, so we would say we reject H naught if Z calc is greater than Z crit equal to 2.33. Okay, so number 5 is we collect our data and we calculate our test statistic. So what data do we need? So we look at our test statistic to figure out what data we need. We need a p hat, okay? We need p naught, and we need n. Okay, so how big is the sample? 105. So that's our n. What is our p hat? Our p hat is our sample proportion, right? So our p hat is going to be the 67 over 105, which is equal to 0.6381, roughly. And what is our p naught? That is our assumed status quo, 0.5. So we have all of our information. Now let's calculate our Z calc. Z calc is just going to be plugging in our numbers into our test statistic. So we just look up at number 3 to figure out what our test statistic is. We have 6.3881. Jesus, pen. Gosh, this pen drives me nuts. It's great, and then sometimes it's not. Okay, 0.50 times 1 minus 0.50, which is really just 0.50, but I'll write it that way. 4 kicks all over 105. We run this whole calculation, and we get 0.1381 over 0.25 over 105, and altogether we're going to get 2.83. Okay, so that's our Z calc or our Z data, whatever you want to call it. So then, am I running out of room? I sure am. So for number 6, we make our decision, our statistical decision. Do we reject or do we not reject? Well, all we have to do is take what we have in 5 and look at the rule for 4. Okay, so what we have in 5 is our Z calc of 2.83, and we reject if that is greater than our Z crit. Okay, well, our Z crit is 2.33, so yes, we reject. So we say reject H naught because Z calc is greater than Z crit, and that's 2.83 is greater than 2.33. And so then what does that mean in layman's terms? That means that Shell management has obtained significant statistical evidence such that they believe more than 50% of their office workers want the 4 10-hour days as opposed to the 5 8-hour days. That's that. Okay? So on a test, you would have to write out number 7. I just don't feel like writing out all those sentences. Okay? But you heard my voice, you heard me say it, so just rewind it and listen back. Oh, excuse me. But essentially, management has obtained significant statistical evidence that more than 50% of the office workers prefer 4 10-hour days. That's that. Maybe in my conclusion, my notes that I put out to you guys, I'll write that kind of stuff in. These videos tend to run really long, and I don't like hour videos. So I think the next time I teach this class, I'm probably going to be trying to make these into more digestible 10 to 15 minute videos and just cover one topic per video as opposed to a whole class lecture. Okay, so now let's move on to problem 7, which is the one where we have the new distribution, the chi-squared distribution. And we'll just read through this problem, and then we'll kind of bop back to the formula and show you guys how to use it. An automotive part must be machined to close tolerances to be acceptable to customers. Production specifications call for a maximum variance in the lengths of the parts of 0.0004. The sample variance for 30 parts turns out to be 0.0005. Using alpha level of 0.05, test to see whether there is significant evidence to show the population variance specification is being violated. Okay. So the first thing we know is that because we're working with variance, we have one test for that. Okay, and that one test, we can look at the grid, is the chi-squared distribution for statistical inference of population variance. Okay, so, and that's what our test statistic is there. Okay, but we know just because we're working with variance that we're going to be working with chi-squared. Okay, and our hypothesis needs to reflect as such. Okay, so let's just start the hypothesis test. So we have H naught, HA. And we want to talk about the status quo we know is the 0.0004. That's what we want it to be, right? And now we're kind of testing against that. But it looks like we are assuming that it's going to be greater than that because of the data that we're given. Yeah, and so that's the thing. So with variance, like, essentially, like, you're always wanting less variance, right? So like the status quo, like, you should always have minimal variance. So the alternative hypothesis, you generally want to make a greater than alternative hypothesis. So sigma squared is, we suspect that it's greater than 0.004. And then conversely, the H naught is less than or equal to 0.004. Our significance level is given to us, so we have sigma equal to 0.05. What is our test? Our test is our chi-squared test. That's just chi-squared equals n-1 times s squared divided by sigma naught squared. So yeah, this sigma we can represent as sigma naught. Okay. Either way, I'm not too particular about it. n-1 times s squared times sigma squared, or sigma naught squared. Okay, so 4 is when we determine our rejection region. So the sigma squared graph looks a little bit different than the normal graph. It's a graph that's skewed to the right, similar like that. Okay, and we just cut it off here because we know we're going to the right. So this is our rejection region. Okay, how much probability do we have in the rejection region? We look up to our alpha for that. So we have 0.05 in the rejection region. And the chi-squared is going to work very similarly to the t-distribution in that all we need to determine a critical value. So our crit is going to be chi-squared times degree, or not times, chi-squared of degrees of freedom and alpha level. Okay, so we need to know what our degrees of freedom is. Our degrees of freedom is always n-1, or in this case it's n-1, and that would just be our sample size minus 1. So 30 minus 1 equals 29. So this is saying we're looking for a chi-squared equal, our chi-square of 29 and 0.05. So we go to our table, we go to the chi-squared table. Nope, that's the F table. Oh, I was going to say, where the heck is the chi-squared table? There it is. Very weird. Okay. So the chi-squared table, we first wanted to find the degrees of freedom. So we scroll down to 29 and then we're looking for 0.05 up top there. And we get 42.5569. Let's go back over. 42.5569. I only take it to that many digits just because that's what is given to us in the problem, or that's what's given to us in the table. It's not really that necessary, but if you have that exact amount, it's not like you calculated that, you just pulled it off a table. So then we would establish our rejection region. So we would say we reject if our chi-squared calc, which we haven't got yet, is greater than, right? We looked at HA for the greater than, is greater than our chi-squared crit, which is equal to 42.5569. So that's how we reject. So 5 is where we gather our data and we calc our test statistic. The data that we need n, we need s squared, and we need sigma squared, or sigma squared naught. Okay, n is 30 from the problem, that's our sample size. S squared is 0.0005, and sigma squared is 0.0004. So our chi-squared calc, or our chi-squared data, whatever you want to call it, is going to be 30 minus 1 times our sigma squared, 0.005, divided by our standard deviation, or our population standard deviation that's assumed of 0.004. That's going to be 29 times 0.005 divided by 0.004, which is ultimately going to give us 36.25. So that's our Z calc. So do we reject? The question is, do we reject? Okay, so we compare what we calculated in number 5 with what we established in number 4, and we look at that rule. It says we reject if we reject if chi-square calc is greater than chi-square crit. Is 36.25 greater than 42.5569? No. So we fail to reject, FTR, fail to reject. We never accept. Okay, so there's no reject accept. It's you either reject or you fail to reject. Okay, we fail to reject because chi-square calc is not greater than chi-square crit, and that's 36.25 is not greater than 42.5569. And then in layman's terms, so for number 7, there isn't significant evidence to show that the specified population variance specification is being violated. So the population variance specification, we don't have significant evidence to show that the population variance specification is being violated. We don't have significant evidence to show that the population variance is greater than 0.0004. Any of that would be acceptable. Just so long as you're telling me exactly what this part in 6 means in terms of problem 7, in terms of what we're actually managerially or real world looking for in this problem, not just math. All right, guys, thanks so much. I will try to get the rest of the problems up for your review as soon as possible. Other than that, we're going to have homework on Chapter 9 due very soon, quiz on 9 due very soon, and then the test for 7, 8, and 9 is coming up next weekend. I believe it's the 10th, 11th, 12th. Wrong. 11th, 12th, 13th, I think. It's next Friday through Sunday. Okay? So yeah, I'll get as much as I can up for review. I'll try to give you guys as many answers as possible on that and work out as many problems as I can. But study hard, enjoy the weekend, and that's that. I hope you all enjoyed this video. Enjoyed, I guess, would be a strong word. But yeah, let me know if you have any questions. Post them on the discussion board. Email them to me. whatever you like. Yeah. All right. Thanks so much, guys. Take care.